Welcome to the Cannabis Cultivation and Science Podcast. I'm your host, Tad Hussey of Kiss Organics. This is the podcast where we discuss the cutting edge of growing from a science-based perspective and draw on top experts from around the industry to share their wisdom and knowledge. Our guest this week is Tom Miles. Tom is the president of TR Miles Technical Consultants in Portland, Oregon, a biomass energy consulting firm, which designs, develops, installs, and commissions systems for processing wood, agricultural, and urban residues. Innovative biomass systems includes pyrolysis, gasification, and combustion, sizing, drying, densification, handling, modification of boilers and gasifiers to improve efficiency and emissions, and systems to recycle nutrients. He has developed heat and power systems in developing countries. His knowledge of ash transformations and biomass led to recycling nutrients using pyrolysis of residues to biochar, which can improve soil health and sequester carbon. He has sponsors and hosted online discussions of biomass energy and biochar since 1994. He is a past chairman of the International Biochar Initiative and executive director of the U.S. Biochar Initiative. Now on to the show. Hey, Tom, thanks for coming on the show today.
Well, thank you. It's good to be here.
Yeah. So, Tom, can we start off with you telling me a little bit about yourself?
Well, I am an engineering consultant in Portland, Oregon, fourth generation in wood products in Oregon. And so I grew up in the wood products industry, if you will. Our firm has been doing mechanical engineering for wood products and renewable energy for a few generations now. And about 15 years ago, after spending something like 25 years working with renewable energy projects, everything from improved cooking stoves to very large biomass boilers, was about the time that biochar was rediscovered. And we always have a certain amount of the charcoal as a co-product or byproduct of combustion, gasification, pyrolysis processes. And when I learned that that biochar could be used to manage nutrients from manures and that sort of thing, I got interested in the use of biochar, production of biochar as a co-product of biomass energy, and the use of biochar for improving soils and managing nutrients. And I worked with my father for about 25 years and have been on my own for about 20 years, and my office is here again in Portland. And my role with the U.S. Biochar Initiative, we created the U.S. Biochar Initiative in 2010, and I've been the executive director of the organization for the last 5 or 6 years. We're all volunteers, trying to create biochar as a business and as a productive enterprise.
That's great. So let's go back a little bit and just cover the basics for folks who aren't as familiar with biochar. A lot of people, when they talk about biochar, they think of the Amazon basin and maybe like Terra Preta, but that's obviously a very different product than what we're producing with biochar, but there is some relationship there. Can you maybe touch on that a little bit?
Well, we can start with Terra Preta. I led a group from the International Biochar Initiative. We had a conference in Brazil in 2010 in Rio de Janeiro, and we went up to the Amazon, where Embrapa, the Brazilian research organization, agricultural research organization, had dug pits for us in the soils that were both Terra Preta and what they call Terra Mulata. And I wound up being the interpreter for the trip, having lived in Brazil and speak Portuguese and so on. And it was interesting to me to discover along the banks of the Amazon. Growing up, we were told that the Amazon had this rich soil. Well, the Amazon has rich tropical life, and that drops nutrients down to the soil. But the soils are actually very poor clay soils. And as it happens, along the banks of the Amazon, where the natives lived over the last 3,000 or 4,000 years, they would grow their crops around their dwellings, and then they would burn that crop residue both wood and grasses and so on, and leave a charcoal residue. And there's some debate as to whether they leave the charcoal intentionally or not. But that then would combine with nutrients in the form of their kitchen waste and sewage and compost together and become combine with the clay soil and become a rich, charcoal-rich, carbon-rich compound. And the carbon would capture the nutrients from the vegetation, and so that it wouldn't leach down and just into the river, but it would stay there. And the natives were cropping annually every year on the same soil without going into the slash and burn into the jungle. And so when the Spanish and Portuguese arrived, they found the natives with a fairly rich native culture and civilization. So that's where a lot of the stories came from, the stories of the Amazon women and the men covered in gold and these kinds of things. The Spanish and Portuguese priests and explorers found that basically these natives had a good renewable regenerative agriculture in a strip not more than about 100 yards wide on either side of the Amazon. But if you follow all the way up the main trunk of the Amazon river, and then it splits into two different rivers, and you add all those soils together, there's an area the size of France that was enriched with this charcoal-enriched soil. And so if we look at biochar, what biochar is charcoal that is made, instead of charcoal, it's made for cooking. The cooking charcoal typically contains tars and oils to help ignite the charcoal. The biochar is you cook it long enough so that you have baked out the tars and oils, and so you have this nice honeycomb kind of structure. And so it has physical properties that are very similar to some of the soil amendments like vermiculite and perlite. And it has chemical properties, and it has surface area that will both absorb and adsorb chemicals and nutrients, potassium and so on, many of the soluble nutrients that are available from not only from manures but plants and so on. And then scientists are now discovering that it also has electrochemical properties which assist in with the metabolism. For example, if you feed biochar to animals, it actually helps the metabolism in the rumen, improves the efficiency of feed conversion, helps keep animals healthy and so on. And so you have these physical, chemical, and biological attributes of the biochar. The biochars themselves are good habitats for microorganisms. And so biochars have sometimes been described as geobatteries, and that they can hang on to chemicals and nutrients. They can help cycle carbon from photosynthesis through the soil solution, and thereby help both with not only with the carbon cycle but also with the nutrient cycle, and help to feed the microorganisms that are so important. So the difference really between the biochar and the terra preta is that terra preta was the full package of basically a composted biochar mineral complex. The biochar plus clay plus the nutrients, and the biochar is the building block. It's just basically the charcoal, but it's charcoal for use in the soil. And the term biochar was coined by our friend, the late Dr. Peter Reed from New Zealand, who felt that we should use a term of charcoal intended for use in the soil rather than charcoal intended for use as a fuel.
Wow, that's great. I wasn't aware of that benefit with the rumen with livestock. That's really interesting. I would be curious.
Well, and the same electrochemical properties also reduce the amount of energy that it takes to transfer nutrients to plant roots. And so it's also partly what's responsible for the efficient, as you well know, wherever we use biochar, in the root zone, in the rhizosphere, we get this really generous root growth, very active root growth. And so now it's being used, for example, as backfill in planting urban trees and landscaping, because early on it helps the tree establish really vigorous root structures. And it turns out that part of the mechanism is that by facilitating the transfer of nutrients to the root hairs, the tree roots, it helps to encourage that root growth.
So how do we make biochar? Ranging from, a commercial operation down to someone who just wanted to try experimenting with home. I mean, you touched on the fact that we don't want to be using charcoal necessarily, and that there is a difference there. Can you touch on how it's made and the importance of the pyrolysis process?
Well, let's start with where I started, and that is with wood. With either wood or grasses. You start with biomass, and the biomass contains about 50% carbon in its structure. And as you heat the biomass, that solid converts to gas. About 80% of the solid converts to a gas, and about 20% of the solid converts to charcoal. And so when you're burning wood, for example, as you can see in your fireplace, you can see the little gas coming out of the fire log. That accounts for about 80% of the mass of that fire log, converts to a gas, and then it burns as a gas, whereas about 20% burns as charcoal. And you can see in the glowing coals, actually the glow in the coals is actually those are more tars and volatiles that are just simply burning on the surface of the charcoal. But the charcoal will burn in direct contact with air. The charcoal doesn't need to convert to a gas to burn. It can burn in direct at the right temperature. It can burn in direct contact with air, and by burning, it's basically oxidizing. It's the oxygen reacting with the carbon and creating CO2. So, in order to make charcoal, we need to heat the biomass, and you can heat it in different ways. You can heat it through what's called pyrolysis, where you heat it in the absence of air. You're not adding any air. And sometimes this is done by putting biomass into a canister and then putting the canister into a fire and then providing the heat from the outside. And you're doing the same thing. You need a place to vent that canister because the solid will convert to a gas and the gas will come out. And when you ignite that gas, you see that it's a combustible gas. You've converted the solid to a form that can burn. The next step is called gasification, and in that case, you're using a third of the air that you would ordinarily use to completely burn the solid, and you can think of it as burning about a third of the wood to convert the rest of the wood to gas. So in that case, in the case of pyrolysis, your char yield is going to be in the 20 to 30% range of the dry weight of the wood you start with. In the case of gasification, the yield typically is in the 15% range because some of the air that you've introduced reacts directly with that charcoal, converts it to CO2, and so it reduces the amount of charcoal yield, and the rest converts to gas, which hopefully you use and recover in some way to generate heat or power. And the third mechanism is simply through combustion. Or ordinarily burning wood, you always have charcoal embers left over, or in a boiler. Typically, you'll have fine charcoal particles that will carry out of the boiler with the combustion gases, and those can be separated in the gas cleaning device and recovered and used as biochar. So, in each one of those cases, you want the material to get to a temperature that's in the centigrade range, in the 350 to 400 to 600 degree centigrade range. For most chars, you get high temperature chars that are above 600 degrees centigrade. To put that in perspective in terms of Fahrenheit, typically the gasification range, where you add a little bit of air, gets you into the 12 to 1400 degree Fahrenheit range. Combustion will get into the 15 to 1800 degree temperature range. And pyrolysis, you hold down to the 800 to 1000 degree range to provide each of those products. Now, the simplest way to make biochar is in what's called a pit kiln, in which you simply dig a pit, a conical pit or a steep-sided pit, and put the biomass in. In Malawi, for example, we have smallholders who farm small plots of land, and in that case, they dig a small pit and take their corn stover from their corn stover or their corn or maize harvest and put it in the pit. And the pit has steep sides, and by lighting the material from the top, it tends to, it's what we call a top-lit updraft. The radiant heat from burning material on the top tends to heat the material that's below it in the pit, and the pit keeps the oxygen from getting to the material, and so the material is sitting there bathing in a pool of so-called pyrolysis gases, the gases that evolve from heating the material, and that tends to promote charcoal production. And so they wind up making a charcoal, and they make it winds up being made at a low enough temperature so that a lot of the nutrients in the corn stover aren't cooked off. And so they take that, eventually cover the pit to cool off the char, and take the char and combine it with a nutrient source, typically manure, at planting, and they plant their corn crop. And so that's one way of making, in a pit kiln, you're basically using the radiant heat from the gaseous combustion to heat the solid, convert the solid to char and gas, and then you use the char beneficially in the soil. Another way of making biochar is in a gasifier, where you add a little bit of air to burn some of the gas to provide heat to char or carbonize the fuel. Again, in Malawi, what they do is use a gasifier to gasify the corn cobs, and they take that char and feed it to their chickens and cows, and wind up with healthy animals with less disease and increase their milk production. A lot of those kinds of benefits. Unfortunately, in the United States, it's illegal to feed charcoal or biochar of any kind to animals. We're trying to change that. We have some feeding trials going on in Nebraska to try to change that. But at any rate, makes a good feed, makes a good soil amendment. In an industrial case, you basically use a reactor, which is sometimes called a retort. Typically, it's an auger, and you heat the outside of the auger to heat the material. You run the material in the auger. It takes about 40 minutes to heat the material, convert the solids to gas, and you burn the off gas often to dry the material that you're putting into the auger. And then there are larger kilns that are rotating drums, and you feed the material into a rotating drum that looks like a cement mixer, a long kiln, and you use either the off gas from pyrolysis, or you use an auxiliary gas, and you heat the drum. You either heat the drum from the outside, or you burn the gas and put the gas through the inside of the drum. And that, again, heats the material, converts the solid to a gas, and you wind up with a char product. And the yields in these different processes can be something in the order of 20 to 30% of what you start with, you wind up with as char. And that char contains about 50% of the energy content that you started with the biomass. So you've converted again, about 80% of the mass and about 50% of the energy into a gas, so it's important to be able to recover that gas and use it to make steam. You can generate power, except that's expensive, but if you can use the steam to heat water for processed water or generate steam for processing the material. In China, for example, they provide an incentive to the farmers to bring their corn stover and their wheat straw to a fertilizer plant. The fertilizer plant converts that stover to char by using the same industrial process of pyrolysis and a rotating drum, and then they will use the off gas to heat the stover to create the biochar. And at the same time, they'll use some of the off gas to make steam, and that steam then they'll use to treat the char, to activate it, as it's called, which will improve the properties of the char. They add fertilizer components to the char,
and then they granulate it, and they sell a granulated biochar-based fertilizer back to the farmer, and they're producing about 500,000 tons per year now, and they expect to get to 3 million tons before long. So they're making a very active industrial use of biochar in China. By contrast, here in the United States, we're producing somewhere in the 50 to 70,000 tons a year. We have about 150 biochar producers and suppliers in the United States, and it's slowly growing as people are discovering the many uses for char and developing markets and understanding, more importantly, the needs of their customers.
So you mentioned a few different methods for making biochar. How does the quality of the final product vary from a soil health perspective when you talk about gasification versus pyrolysis, for example?
Well, if you control the factors of production, if you control temperature and time, then you typically can make a similar quality of biochar regardless of the process. The gasifier chars tend to be slightly higher temperature chars because they're partially oxidized. You've used a little air in the process, and so they tend to burn off more of the chars. They're very clean chars. The wood chars from gasification and combustion work very well for filtration, where you're trying to capture heavy metals from stormwater. They have good surface properties. Pyrolysis chars can, if you cook them long enough, have very similar properties, but then they also have some different surface characteristics, what are called functional groups. And the functional groups have different abilities to attract certain nutrients. But in general, many chars are very similar for most common uses. So if you're using the chars in the soil, if you're using char as an additive to organics and co-composting, composting them together, that's a very popular and very effective use. You use about 5 or 10% biochar by weight or 10 to 20% by volume together with organics, and you wind up with a biochar-based compost. In that case, you can actually accommodate a wide variety of qualities of high temperature and low temperature chars. One of the challenges we've had commercially is that many of the people who've been producing biochars have not necessarily had industrial experience, and they produce an inconsistent quality of char. So it's not necessarily the fact that their char is good or bad. It's just simply that different batches of char maybe have different qualities, and so the buyers complain about truckloads having different qualities. If they're going to use the char in a recipe, in a soil amendment recipe, they want to have at least a consistent product that they can depend on as they add char as a component to other materials for a soil amendment, for example. But there's a lot of what we call a buffering capacity in char, and that there's a certain amount of leeway in quality. And you can make some pretty good quality chars. People look at the kilns. The pit kiln in its metal form took the form of what was called a Kontiki kiln. Generally, we're calling those flame cap kilns because that flame that burns above the pit is providing the heat that's doing the carbonization. And that style of making biochar makes actually a very good quality biochar. It's a slightly oxidized gasification char. But those units, the small portable units, are more place-based applications where you're making char from orchard prunings or vineyard prunings, that sort of thing, for use actually right there in the orchard and in the vineyard. You're not going to take the material very far, and you move the metal carbonizer or kiln around. Where biochars are made in a stationary application, about the size of today's modern charcoal plant, then you're looking at chars that are being shipped pretty good distances to specific applications, and in those cases they use more sophisticated processing and very carefully control char quality for specific uses. And often they'll make what we've been calling designer chars, or chars that are made for specific applications. And what's different about those chars typically is that they're carefully controlled for their size and other characteristics. So if they're meant to absorb mercury and metals, for example, in filtration applications or remediating soils, you might tilt the process a little bit if you've got good control over it to have the chars have slightly different qualities. There's some sort of basic tests for char quality, and that is if you want it to be basically clean and porous. And so if you take the char and crush it in your hands, you hope that it's friable, that it crushes. If you taste the char, or smell it, you don't want to smell a lot of oily, tarry products. You want it to smell pretty clean. And if you take the char and you put your hands in it, you want to be able to wash that char off with water instead of needing soap to wash it off, and that's an indication that it doesn't have any tars and oils in the char and that it's pretty clean. So those are the kind of feel and taste and wash tests that we use just to understand that you've got a char that's been cooked long enough at an adequate temperature so that it's not carrying a lot of tars and oils. The tars and oils can be recovered in a contained device, whether you're heating char in a 50-gallon drum or whether you're putting it through an industrial process. You can condense 3 different densities of liquids. Those gases that are made by heating the char contain some light, we call it wood vinegar or pyroligneous acids, and those are used sometimes as growth stimulants. I understand that you can pay $6 for a liter of wood vinegar in Japan. Use it as a foliar spray, and it turns out that one of the active ingredients in the foliar spray are actually nanocarbons. They're very, very small size carbon particles that can penetrate the stomata of a leaf directly, kind of mainlining biochar, if you will. And that within the wood vinegars there are what they call signaling compounds, or the smoke-smelling, smoke-like compounds that actually act as growth stimulants. So the wood vinegar can be used as a growth stimulant. It can be used straight as the tars, for example, which are heavier, can also be condensed, and those can be used as a preservative. So in Brazil, for example, they will take the mix of wood tars and vinegars. They'll take the tar and they'll dilute it 200 to 1 for use as a wood preservative to protect against termites, and they'll use it 2,000 to 1 with water to use as a growth stimulant. But those products are not widely used here in the United States. We import some wood vinegar products from China. I think there's only about one producer that has industrial uses for wood vinegar here in the United States. But as we look down the road, we look to see more of those products being refined and developed and sold here in the United States.
Yeah. Now, Tom, you'd mentioned, you touched on a lot of stuff there. One thing, though, that I wanted to go back to was how you evaluate a charcoal or biochar. And how would a consumer be able to, tell the difference between these different types of burnt products, whether it be soot or ash or charcoal? Can you touch on that a little bit more?
Yeah, there's actually there are labeling rules about biochars. About 4 or 5 years ago, the American Association of Plant Food Control Officials, which is an association of agricultural departments from each state around the country and in Canada and Mexico, all get together and they decide what constitutes a label for a product. And they decided that biochar, to call something biochar on a label, it had to have at least 60% carbon. And so if you buy a product on a shelf a soil amendment, for example, that has biochar in it, or if you buy straight biochar, it should have 60% or more carbon in the biochar, so that it would have more carbon and less ash. The ash are, natural ash ingredients, calcium, potassium, other components that when you cook down the biomass to biochar, that ash will increase as a proportion of the total because you've reduced the amount of cellulose. Well, some of the chars will have a high ash component. So if you make biochar from the straws or agricultural residues, they start out with a higher ash content. So they're going to wind up with less than 60% carbon. But that doesn't mean they're bad biochars. It just means they have a different balance of ash to carbon. And so you need to understand if a char is coming from an agricultural residue and it isn't labeled biochar, then typically it'll have a slightly higher ash, lower carbon component. So then you use it sort of proportionally. You use it maybe in a slightly different way than you would use a wood ash. It kind of depends on what you want to do with the biochar. If you want biochar to change the texture of a soil or a growing mix, then any kind of a soil additive, whether it's biochar or whether it's a mineral like a vermiculite or a perlite, you really need to add about 25% to a soil mix before you really see a change in texture. But if you want it to be an aid to water holding capacity, that sort of thing, then you may only need to add 5% or 10% biochar to a compost or to a soil amendment. So it really depends in terms of quality. It depends on how you're going to use the chars. There are also chars that are made from manures, and those only have 10 to 20% biochar or 10 to 20% carbon, but they have lots and lots of other beneficial nutrients. And typically not as much nitrogen because nitrogen is cooked off in the process, but you'll have potassium and phosphorus and calcium and a lot of other minerals in the mix. So in terms of biochar quality, if you're buying it in a bag, if it says biochar, then it'll have 60% carbon. Some biochar producers claim that they will have 80% carbon. That's a very high carbon, typically made from a wood product. If you're buying a bulk char and you can do that sort of see and feel test, and it passes that sort of wash your hands and feel it and taste it test, it's going to be a pretty good quality char that's going to be in that 60% or better char range. So, as a consumer, I think what you do, like any other for a soil application, any other growing media, you try it out and you make sure that you're feeding the plants sufficiently with enough nitrogen. One of the things to be aware of is that if you add char to a growing mix, the char will actually preferentially absorb nutrients like nitrogen and so on. And so if your plants go yellow and you wind up being a little chlorotic, you need to add a little extra fertilizer, whether it be an organic fertilizer, a feather meal, or a nitrogen source of some kind, for the biochar to absorb and not take it away from the plant. And that's just really with the initial application. After that, you haven't lost that nutrient. It just simply resides in the char. Ultimately, the organisms will make that nutrient available to the plant. But initially, you want to be able to counteract or offset the nutrient demand of the char itself. It just simply will take up a certain amount of nutrient. I kind of use the analogy of feeding straw to a beef cow, for example. It takes about 4% nitrogen just to supply enough nitrogen for the animal to be able to metabolize the straw. And with char, it takes a certain amount of nutrient just simply to satisfy the appetite of the char, if you will. And so it won't take it away from the plant. But yeah, the quality issue is a challenge. We really, as an organization, as an industry, we need to find ways of identifying grades of biochar suitable for particular applications, and that's really the challenge. There are many different qualities of char that can be used in different ways, but it's matching the quality of the char to the application is really the key.
Yeah, I do want to highlight that for people because I think it is important if you're purchasing biochar that you do your homework and know what you're buying. A good biochar company should be able to provide you with testing and information about the product that they're producing, and it should be consistent. I've seen this problem in some of the industries that I'm more involved in terms of certain people, putting out product at lower cost that may not be of the same quality. And so it's really important to, I think, do your due diligence, especially with an industry like this that's sort of an emerging technology as people are still learning about it.
Well, the other thing, too, is simply really has less to do with the biochar than it does to do with the fact that it is a new industry. You get people who have great ideas about biochar. They over-promote the product, and then they deliver a product that doesn't help. They don't show the customer how to use the product appropriately, and so things fail, and then everybody has a bad idea about biochar in general. But it typically takes 3 to 5 years to start a business, and it takes 3 to 5 years for people to get used to developing a product that is useful and matching the product to the customer. And so I can always tell when a biochar producer calls, I can typically tell whether that producer is gotten to the point where they really understand the needs of the customer.
Yeah, I mean, we've been using biochar now, oh boy, I want to say close to a decade. My father, got really, as you already know, I'm just sharing this for listeners, got really involved with the Kentucky kiln. We have a Kentucky kiln that we use fairly regularly to burn material. And then we've been working with Black Owl Biochar as the product source for us in our soils, and we've seen wonderful results. I've seen, on average, across a variety of different growers, somewhere around the range of like 8 to 10% better plant growth and yield with the addition of biochar in the mix.
Well, and one of the nice things about the Black Owl Biochar is that the producer is a user producer, and that she was growing organic vegetables when she discovered biochar and growing peonies, and it was a result of her doing some testing of adding biochar to her favorite growing mix with peonies that got her excited about biochar because she saw the positive benefits, and then got into the business of producing it. So her criteria for biochar quality comes from the point of view of a consumer, a user. And similarly, other companies that have incorporated biochar into their product, like Kellogg Garden, for example, in California, they have about 1,000 outlets. They're a pretty good-sized company that's been in business since the 1930s. They spent about 4 or 5 years experimenting with biochar before they decided to incorporate biochar into a product with their label on it, because they needed to protect the integrity of their label. And they've been very happy with the products they make. They make a couple of biochar amended products. There are some organic products. One called Sustain that has taken their basic organic fertilizer and added biochar to it, and their customers are very happy. So again, there are some quality producers, and at the other end of the spectrum, there are people that put together what they think is a quality material. It may have worked with in their own soils in their own garden, but when they put it out and sell it to the general public, they may or may not be very good about explaining how it should be used and in what soils and circumstances.
So can you talk a little bit, Tom, about why biochar is so important from an environmental perspective? I mean, when I hear the idea of burning wood for the sake of improving my soil, on the surface, that sounds like a really negative environmental experience. Can you talk about why it's important and beneficial?
Well, the carbon in making biochar, you're converting the carbon that has been developed through pulled out of the atmosphere through photosynthesis, and you're converting it to a form that can be, as they say, recalcitrant. It'll stay in the soil for a long time. So you're really removing carbon from the atmosphere, and you're putting it into a form where you can put it in the soil, and it will stay in the soil. And not only that, the biochar will catalyze the whole biological process. So I always like to say that the magic of biochar is biology. You're really stimulating the biology by improving the ability of the plants and so on to photosynthesize carbon and remove it from the atmosphere and cycle it through the soil. And at the same time, you're taking a renewable source of energy and you're converting it either to energy or to chemicals. And there's a great deal of research. There are about 3,000 peer-reviewed academic papers a year on the use of biochar in different applications, and about half of those are devoted to improving the conversion processes of making biochar and recovering more and more carbon. So typically in a Kentucky kiln, which really is an engineered pit kiln, you're recovering about 50 to 60% of the carbon that it was in the plant to start with. And what we're finding now is ways to recover even more of that carbon and put it into forms that are recalcitrant, that won't break down for thousands of years. And that was one of the exciting things to soil scientists 100 years ago when they discovered the terreprate in the Amazon, and also the biochar that's been used in man-made or anthropogenic soils in 700 or 800 locations around the world. And that is, here you could put carbon into a form that was going to last in the soil for literally thousands of years. So it's carbon removal. We've seen the first sale of carbon credits for using biochar from a producer here in the United States selling in the European market, the volunteer market. And we see other methodologies and other markets evolving for trading biochar on the carbon market, and that's because it's got a value of removing carbon from the atmosphere. So there's that carbon side, and then in addition to that, there's the biological side. And as evidence of the nexus of the two, of the carbon and the biology, where they've been doing trials where they've been looking at the degree to which carbon is removed from the atmosphere, where they've used biochar over a 10-year period, they find that far more carbon is actually accumulated in the soil than just the amount that counts for the biochar. So there's typically 10% or more increase in carbon sequestration from having used biochar to stimulate the biology and truly regenerative agriculture. So we get some real benefits. The challenge with biochar, part of the challenge with biochar today, is simply the cost of making it. When you're making it in the smallholder situation, in thousands of smallholders in Asia, and Africa, and South America have been using biochar as a soil amendment, and there they make it in very simple kilns, and they use their own labor, so they don't have a lot of capital invested, and they can benefit from its attributes pretty directly. In developed countries, in Europe, the United States, it's growing more slowly as a material, simply because we do things in an industrial process that requires labor and more expensive inputs in terms of electricity and so on. And so the biochar becomes fairly expensive. So we're looking forward to those carbon markets helping to offset the cost of biochar so it can be less expensive to our agriculture. And on the carbon side, we're also seeing products that are incorporating biochar into building materials where it will also last for a very long period of time. So it's being incorporated into cement and asphalt, being incorporated into plastics, a number of different combinations. That liquid portion is being polymerized into, you might call it natural plastic-like materials, which will last for a very long time. So we get this carbon benefit as well as getting this agronomic benefit and the biology.
Oh, that's great. I didn't even know about the building materials side either. That's really interesting. I've been focused on the agriculture uses. A couple other things I want to touch on that you kind of danced around too was this idea that it'll help fight global warming. It's improving our soil fertility, which you talked about. And then the thing that my father was most interested in is this idea of reducing agricultural waste and also forestry waste, where we could take when the logging occurs, they can come back in and grab some of that, I believe it's just called slash material, and burn that to reduce the risk of forest fires while also sequestering the carbon that can then be applied back onto those lands or potentially sold as a byproduct to an agricultural source.
Our principal supporter for the U.S. Biochar Initiative is actually the U.S. Forest Service. They're quite interested. As you know, the wildfire hazard is quite large. We had 57,000 wildfires last year in the United States, covering 10.3 million acres. The year before that, we had about 43,000 fires covering about 4.5 million acres, and I think the year before that, we had about in the 50,000 fires again, covering about 8.5 million acres. And according to the insurance folks, there are 4 million homes that are in danger from wildfires. And of course, it varies from state to state, but pretty much across the country, there are serious problems with wildfire, and so from the forest residues. And so it's the buildup of not only the forest residues that are left from logging, but also simply the buildup of poorly managed forests. We have this great collection of forest fuels, which causes the wildfires. So the Forest Service has been interested in the conversion of these lower value materials, which can't be converted into solid wood products for building and so on, into biochar, and biochar for use in applications to improve forest health. So biochar is a great filtration media for cleaning up waterways. And in our natural forests, we have about 300,000 abandoned mine lands that are leaching chemicals into waterways. And by taking some of these forest residues, converting them to biochar, we can actually filter and permanently tie up those minerals that cause problems. There's restoration work going on in places like Colorado and so on that have demonstrated this. And here in Oregon, in southern Oregon at a nickel mine, various other mines. So we're working with the Forest Service looking at locations where biochars can be used for improving rangeland, for example. They found in the Rockies, they found that by adding biochar to grazing land, they can improve and increase the water retention in grazing land, so they can actually get an additional month of grazing by adding biochar to the grazing land in the forest. We also have, of course, the crop residues. Here in Oregon, we export about 700,000 tons of our straw from our grass seed harvest to Japan and Korea and Taiwan as a feed supplement, as a dairy feed supplement. But that's more difficult with straw residues like in eastern Washington, where you have wheat straw that has a different texture and application. We've finally seen in eastern Washington now there's a paper mill that's making paper from wheat straw. There hasn't been a market for that for the last 30 years. 40 years ago, we did have paper mills that were making paper from straw, but we've been importing wood from around the globe at a very low cost, and So that hasn't been an option. Well, there are also crop residues and processing residues like manures from anaerobic digestion, the digestate from anaerobic digestion that can be converted to biochars. And so the combination, if you look at the U.S., we have supposedly, according to the Department of Energy, about 1 billion tons of both residues and potential energy crops of various kinds that could be converted to fuel and other chemical products and byproducts. And biochar can be a co-product of some of that processing. So potentially we could make biochar as a co-product. There's a plant in Oregon that will be making, in Lakeview, that will be making jet fuel from wood, and one of the co-products will be biochar. So here we can help work on improve the increased renewable energy, at the same time find a home for the some of the residues and some of the parts of the residues that can't otherwise be used, heavily barky residues or some of the crop residues and manures and waste and so on, by converting them to energy and biochar.
That's really interesting. I look forward to following up with you about this jet fuel option and the biochar that's coming out of that. That's wonderful to hear about more renewable energy sources. Just to tie everything back together, though, I wanted to ask you, so we had talked about, from a user perspective, growing plants and in regards to soil health and that use for biochar. If we start, for example, in our soils, when I talk about making soilless media, essentially, we're at 5 to 8% by volume of our total mix. You mentioned people using biochars up to 25% and considering it more as a portion of your aeration, essentially, in your soil, so using it to control, gas exchange, air exchange. There are some properties of biochar that I think we should touch on, which is the fact, like you mentioned, it has a very high cation exchange capacity. It tends to be alkaline, which raises your pH. How are these things sort of accounted for on a practical level when combined into a soil?
Well, to start with, most of the biochars are analyzed. The system of analysis was developed by the International Biochar Initiative, and there are certain laboratories, like control laboratories in California, that follow the International Biochar Initiative. Protocols were identifying other laboratories around the country that are capable of analyzing biochars. And so you do get numbers or reference numbers you can use on alkalinity, on cation exchange capacity. We have a tool on the International Biochar Initiative website where you can plug in the properties of your biochar, and it will suggest uses as a soil additive or as a growing media. It looks at particle size, all the different characteristics. As part of as far as growing media is concerned, for example, in one case, we looked at biochar as a co-product from gasification for use in a nursery growing tree seedlings. And the nursery was using typical, what used to be called the Cornell mix, which was 50% bark, because bark is cheap, 25% vermiculite, and 25% peat. And so we started substituting. We did some tests substituting different levels of biochar from the gasifier, substituting the biochar for the vermiculite, looking primarily at replacing the sort of physical properties of vermiculite with biochar. And we found that we could add up to 25% biochar until we ran into the situation where, because of the instead of using peat, we were using compost as a peat substitute. The compost happened to be alkaline, and so we ran into an issue with one of the tree. I think it was sugar pine, one of the tree species. One of the fun parts about doing experiments in a tree nursery is you've got hundreds of thousands of trees to look at in the greenhouse as you look across, and you can tell whether a species has a particular problem or not. But we were able to actually go to high rates of substitution with the biochar, again, relying primarily on the physical characteristics of the biochar. But in that case, you've got fertigation, so you're actually supplying the fertilizer and so on to the tree seedlings, and you're not depending on, other attributes of the biochar. But typically, it's interesting because 5% keeps coming up again and again as sort of the best, between 5 and 10%, sort of the best rate of application of biochar to, regardless of whether it's an organic media or a soil mix. And that seems to be a level where you get the best benefit.
That's interesting. Yeah. Now, relating to this tree trial you did you see other issues associated with the high rates of biochar besides just alkalinity? Did you have to treat it with some nitrogen prior to adding it in, so it didn't cause plants yellowing and nitrogen robbing?
Well, again, in that case, with the seedlings, you've got a fertigation type situation where you're constantly adjusting and balancing nutrient levels. So we probably did increase nitrogen initially to balance the effect of the biochar, especially at those very high rates. In other words, the high rates, to give you an example, there's a composting operation in Missouri that's using a lot of biochar because the more biochar they use, the more food waste they can take in. Well, food waste has much higher nitrogen and higher nutrients than their typical organics in the composting process. But what's interesting, and they'll openly talk about this, is that the more biochar they use, the more food waste they can use. The food waste has a higher tipping fee, so that helps their economics. They wind up making a richer compost that they actually charge twice as much for compared with their regular compost. So but they wind up with, after composting, they wind up with, they advertise 16% biochar by volume. So that's about 8% biochar by weight. So you're still back in that 5 to 10% range. And that seems to be sort of a magic range. And it not only just seems to be a magic range, it's been very well documented and tested in multi-year trials and research in Europe and here in the United States.
So last question. For someone who's really interested in learning more, passionate about biochar, can you talk a little bit about how someone might get involved with the International Biochar Initiative, or IBI?
Yeah, we have two organizations. We have the International Biochar Initiative, and we also have the U.S. Biochar Initiative. The International Biochar Initiative was created back in 2007 with the idea of developing standards and practices for the use of biochar for carbon trading. In 2010, we created the U.S. Biochar Initiative with the idea of focusing primarily on the needs for the use of biochar in North America. So you can go to biochar-international.org for the International Biochar Initiative, or just Google International Biochar Initiative. Or the U.S. Biochar Initiative is biochar-us.org. For the U.S. Biochar Initiative, we have a YouTube channel with about 60 videos that we put together last December in what we call the National Biochar Week. We've held about seven conferences and one virtual conference. We have a monthly newsletter. The U.S. Biochar Initiative does. You can sign up for the newsletter on our website. We're basically a volunteer organization. We rely on donations and grants from Forest Service and other sources for promoting the use of biochar. We work very closely with the International Biochar Initiative, and so we actually work in an international community, if you will, very active biochar community in Australia and in Europe and in China and in Latin America, connecting all these folks. I chaired the International Biochar Initiative for about 4 years, and for the last 5 years I've chaired the U.S. Biochar Initiative. So we're slowly Our biggest challenge is educating folks. We also have a biochar discussion group at biochar@groups.io, and that's a discussion list that I've hosted since 2006. We have about 1,000 people online and some very knowledgeable and experienced people in biochar. And the challenge with those listservs or discussion lists is always you have to ask the question to get an answer, and sometimes you'll get answers from armchair experts who really don't know what they're talking about, but we have a pretty high quality of expertise and exchange on the list that I'm pretty proud of. So, number of ways by land or by sea of getting the message, and we'd certainly welcome people to join us at the International Biochar Initiative, which is a membership organization, and the U.S. Biochar Initiative, which is basically just an active community.
Well, that's great. I sure appreciate your work in promoting this technology and renewable resource for people. And I'll be sure to put those links on the podcast page as well for people who are listening. And I look forward to staying in touch and hearing what the future holds for biochar.
Well, thank you. We certainly enjoy your participation and promotion and so on of biochar, and we think that everybody can benefit. So.
Oh, absolutely. I love using it in our soils. I see such a difference in the quality of the vegetables and other plants that we grow in it. So I can't say enough good things about biochar. So I don't think we'll ever stop using it. It's so great. So yeah. Well, thanks again. I will stay in touch and appreciate your time today.
Great. Thank you very much.
All right. Bye, Tom. That was Tom Miles, and you are listening to the Cannabis Cultivation and Science podcast. Don't forget to check out the podcast page at www.kisorganics.com. Just click on the Learn tab, then Podcast. And by the way, we carry the Black Owl Biochar from Biochar Supreme, which in my opinion is the highest quality, most researched, and most consistent commercially available biochar on the market. We've used it in our soil mixes for years now and also have it available by the cubic foot bag or by the yard. Thanks for your support and happy growing.